Hello everyone. I'll be discussing problems related to in-out propagated noise scenarios, and I will discuss one of the possible solutions for it. Consider a number of machines that induce noise, such as industrial-grade machines or compressors. The noise generated by these machines can be eliminated by placing an encapsulating structure around the noise source. To further reduce the noise, active structural acoustic control can be applied by placing microphones or sensors and actuators mounted on the plates of the structure, driven by a control system. This option can further reduce the noise depending on the type of the interior noise. There are difficulties in implementing such systems for large-scale applications where the computational capacity is limited. There are many workarounds to solve this problem. This include using partial update algorithms or possibly distributed control algorithms. An example of this would be one of the diffusion algorithms. In most scenarios, noise control casings are typically underdetermined systems, where the number of actuators are higher than the error sensors. That is because this configuration grants more stability and more attenuation for the system. However, this can further increase the computational complexity. To answer the research question, for a predefined system, some actuators can be disabled during the control process, depending on the noise characteristics. However, this leaves us with another question where we have to determine which actuator can be disabled. Here we can disable the adaptation of some control filters based on information from the secondary path plant models. This selection process is supported by the reference signal in case of time-varying noise conditions, and it is also a scheduled process, meaning that it is performed every nth iteration. There are two selection algorithms. The first algorithm is based on selecting a subset of actuators that are highly coupled to each sensor. In other words, maximizing the individual energy contribution. While the other algorithm is based on selecting a subset of actuators with the least phase delay, which translates to selecting actuators that have faster response time. This is a physical description of the system. Here we target vibroacoustic control of the lightweight casing, which is made of aluminum material. Each plate is mounted with 4 actuators except for the top plate, which leaves us with 21 actuators in total. There are 5 microphones in this system. Each microphone is distributed and is placed corresponding to each wall of the casing. For detailed positioning of the microphones and actuators, please refer to the publication. This is an equivalent schematic for the system. Here we have a reference sensor capturing the noise source, and we have multiple error sensors that are coupled with the primary noise and the secondary sources, which are then coupled by the acoustic path models. The output signals are computed by the adaptive filters inside the control system block. This is an expansion of the control system, where each control filter is updating according to the selection vector that was computed previously from the selection algorithms. The control algorithm used in the simulation is the normalized multiple error filtered XLMS algorithm. The simulations were performed in two different parts: time-varying and non-time-varying noise conditions. For the time-varying conditions, 3 simulations were performed. The first one is a chirp signal, the second one is a time-varying harmonics, and the third one is a stochastic noise. All the simulations were performed under 10 minutes duration. Each simulation has an added 30 decibel sound to noise ratio as background noise. This was done to replicate signal condition of a real system. In chirp signal scenario, the starting frequency is 50 Hz and the ending frequency is 300 Hz, which leaves us with a rate of change of about 0.4 Hz per second, which is considered slow for this case. This is because the control algorithm originally does not grant high convergence with spatially larger applications. And this low convergence speed is also caused by the time-varying noise. In this figure, each plot is associated with the sound pressure level obtained at each microphone. The last plot represents the mean sound pressure level. Similar attenuations can be obtained using a set of 15 actuators for both methods. This is compared to the full-scale system, which is using 21 actuators. In case of time-varying harmonics, the simulation considered 10 harmonics, with the fundamental frequency starting at 30 Hz. Similar attenuations can be obtained using a set of 9 actuators for the LPD method, and a set of 12 actuators using the MAC method. The rate of change of the harmonics depends on its order. The expression of rate of change of the frequency is given as 0.1 k over pi Hz per second, where k is the index of the harmonic. And for stochastic noise, band-limited white noise is considered since the attenuation is highest at frequencies starting from 200 to 300 Hz. A set of 15 actuators produced similar attenuations for both methods compared to the original full-scale system. In case of time invariant conditions, the simulations performed here consist of singleton simulations. Each simulation is stepped by 5 Hz, starting from 10 Hz to 500 Hz. Most of the simulations consider an upper frequency bound of 500 Hz. Going above this limit can introduce instability for this model. For this simulation, a set of 15 actuators can similarly produce the same attenuation as the original full-scale system. This is a summary for the computational complexity required for each method compared to the full-scale system. In the chirp signal scenario, the computational load can be reduced by about 5.6%. This was caused by reducing the adaptation load. For time-varying harmonics, using the MAC method, this leaves with a reduction in the computational complexity of about 25%. And using the LPD method, this leaves us with a reduced complexity of about 34%. As for the stochastic noise, using both methods, this reduced the computational complexity from about 17%. Given a short summary, the LPD method generally provides a better convergence rate, and the MAC method provides a better steady-state attenuation. Here we have a noticeable reduction in the computational load in case of time-varying harmonics due to less switching effect between the subsets of actuators. And generally speaking, the adaptation of control filters can be reduced from 21 actuators to 15 actuators for most cases. Apart from the summary, future work could consider these selection algorithms. It can be used in distributed control algorithms such as the diffusion FX-LMS algorithms. This can be done by determining the neighboring nodes using the secondary path responses. Thank you for your attention.
For the out-in problem of the Innova project, we will introduce the current solutions and our recent advancement. The out-in noise reduction concept focuses on minimizing the impact of external noise on our quiet internal spaces, like car interiors or airplane cabins. By combining advanced passive and active techniques, we aim to create a more comfortable environment. To address the challenge of external noise entering our internal spaces, two main strategies are employed: controlling noise transmitted through structures and controlling noise transmitted through the air. Structural noise control is used to minimize noise propagation through materials. For instance, in airplanes, it reduces vibrations in thin-walled structures like the fuselage, making flights quieter. Active noise control can directly cancel sound waves within the space by generating worse sound waves, similar to noise-canceling headphones. Based on the areas we want to control, noise reduction techniques are divided into global and local control strategies. Global control aims for system-wide noise reduction by managing noise along all paths. This involves sensors and actuators distributed across the entire environment. Local control focuses on specific areas, such as individual passengers. For example, handrest-mounted devices can create a quiet zone for passengers in noisy environments, like airplanes or cars. Plateau algorithms have been instrumental in ANC. LMS is suitable for simple systems and narrowband noise control with low computational requirements, but slower convergence. FXLMS, widely used for ANC applications, balancing computational complexity and effectiveness. RLS and FXRLS, ideal for dynamic and precision-critical noise scenarios, offering fast convergence but at a higher computational cost. Frequency domain methods, effective for high-frequency noise with reduced computational load. Neural networks, suited for complex, nonlinear, and broadband noise environments, though they demand significant computational resources. Data-driven methods can deal with nonlinear reality in ANC systems and are more adaptive to complex environments. But it's still a new area that needs to be sufficiently explored. Recently, we have explored deep learning-based ANC, which has shown superior performance compared to previous techniques. We will now present this work in detail.
The noise box is a structure specifically designed to serve as a test bench for analyzing and benchmarking noise reduction solutions in vehicle interiors. It enables the testing of materials, structure, and control strategies to address noise issues inside the car. This system was developed to meet several key requirements. It must be representative of the different noise pathways found in vehicles, including panel vibrations, cavity acoustics, structure-bound noise, and airborne noise. It should be straightforward to model and analyze with simple geometry and well-defined boundary conditions. Additionally, all geometric, material, and physical parameters must be fully specified. The noise box uses a simplified plate cavity system, a rigid box with a single flexible panel. The cavity simulates the vehicle cabin and flexible panel represents the vibrating car body. This setup captures the coupled dynamics between the structure and the acoustic field within the enclosed space. The objective of this experiment is to study the control of noise penetration from the external environment into the noise box. To simulate external disturbance, a loudspeaker is placed outside the cavity and an accelerometer is used as a reference sensor. The accelerometer is positioned at the top left corner of the aluminum panel to avoid nodal points. Inside the cavity, there are 4 microphones, but only one is used for a single-channel control algorithm. These components are essential for calculating the frequency response functions, FRFs, of both reference path and primary path. For the secondary path, a loudspeaker installed inside the cavity acting as a cancelling loudspeaker. Both loudspeakers are driven by random signals to simulate the disturbance and control conditions. The transfer functions of the reference, primary, and secondary path were derived in 2 steps. First, we activated the loudspeaker outside the cavity, collecting data from the accelerometers on the aluminum panel and the microphone inside the noise box. This data allowed us to calculate the reference path FRF using the signal sent to the loudspeaker as input and the accelerometer reading as output. The magnitude of the reference path frequency response function is in meter times millivolt per square second. To determine the primary path FRF, here the input is a loudspeaker signal and the output is a microphone signal. Its FRF magnitude is in Pascal per millivolt. Finally, for the secondary path, we use the signal sent to the loudspeaker inside the cavity at the input, with the microphone signal serving as the output. The secondary path FRF is also given in Pascal per millivolt. Each frequency response function was computed from 100 to 2000 Hz, with a step of 1 Hz. The AAA for Adaptive Andalus-Anderson algorithm was used to identify each frequency response function. The state space coefficients are used then to implement the environment in the control algorithm. In our case, the control algorithm used is SFANC and NLMS, a hybrid version of SFANC and NLMS. I will first explain SFANC and then the full SFANC and NLMS approach. Selective Fixed Filter Active Noise Control (SFANC) is a noise cancellation method that involves pre-training a database of control filters which are then selectively applied during operation. It operates in 2 stages: offline filter pre-training and online noise control. During the offline stage, a dataset of synthesized noise tracks is used to simulate various disturbances. These tracks cover a wide range of frequencies, ensuring that diverse noise characteristics are included. The control filters are obtained using an adaptive algorithm during this stage, and they are then stored in the database for later use. The online stage, the system analyzes the primary noise and selects the best filter from the database. This reduces the computational complexity and improves the response time, making it ideal for non-stationary noise. By separating adaptation from running time, SFANC enables efficient noise control and low-power hardware, making it suited for dynamic environments. In our case, neural networks are used to select the most appropriate filter, further enhancing efficiency in various noise conditions. In this approach, deep learning is used for both features extraction and selecting the most appropriate pre-trained control filter on the type of the noise to be mitigated. A convolutional neural network, CNN, running on the coprocessor determines the index of the optimal control filter for each specific noise type. The controller then adjusts the filter coefficient according to this index. The model we use is the M6 RES architecture. It's 1D CNN and its architecture is presented in the figure. To train the CNN, we create a dataset of 80,000 synthetic broadband noise. Each noise lasted 1 second and varied in a frequency band. Each noise sample was labeled with the index of the control filter that achieves the best noise reduction for that disturbance. The dataset was split into 80,000 samples for training, 2,000 for validation, and 2,000 for testing. With this architecture, a validation accuracy of 99.4% was obtained. Finally, we compared the performance of our 1D CNN against several other 1D networks including M3, M5, M11, M18, and M35 RES. This model also works with raw acoustic waveform. A detailed comparison of results can be found in the table. Concerning SFANC and NLMS, the system operates by capturing noise at a rate of 16,000 Hz, meaning it processes 16,000 samples per second, essentially 1 frame of data per second. A dedicated coprocessor analyzes these frames using 1D CNN, which identifies the most suitable pre-trained filter for noise control. Once the appropriate filter is selected, its coefficients are fine-tuned using NLMS algorithm. This refinement ensures that the pre-trained filter obtained through the SFANC approach is optimally adapted to the current noise environment. The coprocessor operates at the frame rate selecting filters, while the real-time controller works at the faster sampling rates, continuously updating the filter. By leveraging the strength of SFANC for pre-training and NLMS for real-time fine-tuning, the system adapts efficiently to varying noise conditions, steadily improving noise reduction performance. In our simulation, we use a single-channel system. The system operates with a sampling rate of 16,000 Hz and a control filter length of 4,096 taps. For modeling, we rely on the state space coefficient introduced earlier as a reference, primary and secondary path. The system includes 7 pre-trained control filters, each corresponding to specific frequency presented in this figure. These filters were derived using an NLMS algorithm with a step size of 0.0001. The resulting 7 pre-trained control filters labeled C1 to C7 are optimized for their respective noise bands. Finally, this figure illustrates the frequency spectrum of these pre-trained control filters, showing how each one is tailored to handle a specific noise range. To evaluate the efficiency of the algorithm, we tested it with both stationary and non-stationary noise. Stationary noise was represented by a Gaussian white noise filtered between 20 and 500 Hz. For stationary noise, the SFANC NLMS algorithm demonstrated significant advantages over NLMS and SFANC. The results showed that SFANC and NLMS achieved lower error amplitudes and effectively controlled the resonances. Analyzing the power spectral density, PSD, SFANC and NLMS attenuated the resonances peaks at approximately 160 Hz, 230 Hz, and 360 Hz, which SFANC alone could not address. Additionally, SFANC and NLMS starts controlling noise immediately due to its adaptive properties, while SFANC begins after 1 second. On average, SFANC and NLMS achieve a noise reduction of 7.73 dB compared to 6.91 dB for SFANC and 3.84 dB for NLMS. For non-stationary noise, the algorithm was tested with sounds like a motorbike or handheld drill. The SFANC and NLMS algorithm consistently outperformed SFANC and NLMS, showing greater adaptability to changing noise characteristics. In the frequency domain, SFANC and NLMS achieved lower amplitudes, particularly between 20 and 500 Hz, demonstrating its efficiency. Unlike SFANC, which showed a collapse in performance at certain moments, SFANC and NLMS maintained stability and robust control throughout. The results obtained for different types of noise are summarized into the table, further confirming SFANC and NLMS as a more efficient solution for dynamic noise environment. Concerning future work, we plan to focus on deep learning-based active noise control algorithms. These are not traditionally adaptive algorithms, but rather a deep learning approach to generate anti-noise directly. This approach is particularly interesting due to its ability to capture spatial acoustics patterns and handle nonlinearities effectively. Additionally, for greater simplicity and reduced computational loads, direct data-driven methods can be employed. These methods are advantageous because they eliminate the need for system identification and directly approximate the optimal active noise control. That's all for this presentation. Thank you for your attention.